Yeah. Ooh, that's loud. Okay.
Raz, dwa, trzy.
Fine. Should we put it off and then on again on this one? Okay.
So, welcome everyone. I hope you recovered during the lunch break. And now you're ready to welcome our first speaker, Elena, who tell us about understanding cosmology with galaxy cluster profiles. So the floor is yours.
Thank you. Okay, happy to be here. My name is Elena Hernandez, and I'm a cosmologist, and I work as an AI researcher at the Applied AI Institute for Europe. And today we're going to talk for a bit about, well, how can we use AI to better understand the origin and evolution of the universe? So as cosmologists, there are actually two main questions that we try to answer. The first one is, how did the universe form? Like, what were the initial conditions that led to the universe? And the second one is, how did it actually evolve into the structures that we see around us today? Like, for instance, galaxies or clusters of galaxies. How did they come to be? And those are actually very tough questions to answer. And the reason for this is twofold. The first one is time. So the processes that shape the universe, they play out over millions and billions of years. So whenever you look at a galaxy in the sky, you're like seeing a picture, a snapshot of that galaxy at that moment, but you don't really know how it looked before or how it would look in the future. And that makes it the whole thing quite complex. And the second problem is complexity. What we actually see is not the result of a clean process, but it's actually the product of many violent, highly nonlinear phenomena that all interact at once and create these structures. For instance, supernova explosions, black holes and their feedback in the medium. We have also relativistic jets. We have collisions between galaxies, even collisions between clusters of galaxies, which are the most energetic events in the universe. And all these play a role in shaping the final properties of these structures. And so that's why the last, I would say, 20 to 30 years, astrophysicists have dealt a lot with trying to understand this and also try to understand this through simulations, because simulations allow us to basically create these galaxies and these galaxy clusters and see what actually happens and how they come to be. So to give you some examples of some simulations that are out there, we can do isolated simulations of galaxies and even collisions of galaxies. So these are the kind of things that we can simulate. We can even simulate patches of the universe with thousands of galaxies in it. So that to show you what you're actually seeing, all these points that you're seeing here, those are galaxies. So we have like thousands of galaxies there. And you're seeing a cluster of galaxies form. So what you see here is a cluster of galaxies that actually exists in our universe. It's called the Coma cluster. And this is a simulation on that galaxy cluster. And you're seeing the whole evolution of this galaxy cluster from almost the beginning to now, like 13 giga-years in just a few seconds. So these are the kind of things that we can do now with cosmological simulations. So as I was saying, every structure that we see in the sky is shaped by two things. We have the cosmology, which is the overall ingredients and the initial conditions of the universe, which is actually what, as cosmologists, we mostly care about. And then we have also these astrophysics events or phenomena, which are messy, are local, and nonlinear physics. So basically what we have is an inverse problem, right? We observe the output, these galaxies or these clusters of galaxies, and we want to know is the parameters that actually generated them. And this is something where machine learning can actually help. So we're going to see how it actually does that. So this is the idea. We want to build a model that takes a structure in the sky. In our case, it's going to be clusters of galaxies. And it will look, or we will look at its measurable properties. And based on that, it will predict the parameters that matter most in cosmology. For us, it will be these 5. So it's omega m, which is how much matter there is in total in the universe. This includes dark matter. Omega baryon, which is the second one here, which basically is how much luminous matter there is in the universe. We're also going to try to infer h naught, which tells us how fast the universe expands and is related to dark energy and its nature. And also 2 parameters here that have to do with the initial conditions of the universe, how lumpy the initial conditions of the universe were, and at what scales they actually were, these initial perturbations that we had at the beginning of the universe. So to train a model like this, we need examples where we actually know the ground truth. And these examples, we only have them, basically the ground truth, we only have them in simulations. So what we're going to try to do is we're going to build a set of cosmological simulations with different universes that have different values for those parameters and different astrophysics. And we're going to train a model on actually identifying or actually inferring those parameters so that one day we can actually take real clusters of galaxies and infer what are the actual parameters of our universe, the universe we live in. To put it into context, we had some prior work where we used galaxies to do this. So we used graph neural networks to localize galaxies, and based on these graphs, basically try to infer the parameters. And we only were able to infer one parameter here, omega m. And also with properties of galaxies, we also tried this. So at the moment where we did this study, the only parameter that we were able to infer was this one here, the omega matter one. And the rest, it was impossible. So we were wondering, can we actually do better? And to do that, we built a new set of 768 simulations. They were focusing galaxy clusters, or maybe reproducing galaxy clusters, spanning a 28-dimensional space. So we have these 5 cosmological parameters, and then we have an extra of 23 parameters in the simulations that control things like how the supernovas evolve and how much energy they inject, or things like how the black holes basically inject energy into the medium, things like this. So astrophysical events, basically. We have this 28 parameter space, and we have galaxy clusters basically localized in this 28 parameter space. The simulations took around more than 1 million CPU hours, between 1 million and 10 million. I don't remember exactly the number. I'll have to check again, but more or less like this. So you see at what scales of computational time we're actually working here, and the expenses as well. And actually, the data is available. So it's open source. So if you actually want to try and do something with the simulations, you can do it, because the snapshots are there. And you have here, that's the name, and that's also the link. And I mean, if you want, you can just send me an email, and I will send you the link. Okay, so what is the method? From each simulated cluster, you're seeing a galaxy cluster here. From each simulating cluster, we're going to extract a set of radial profiles. And this will be, this is basically quantities and how they change with radius, right? We're going to make spherical cells. And from this, we're going to calculate for each spherical cell the value of temperature, metallicity, X-ray emission, gas density, and Compton-wide signal pressure, basically. And then, because 768 galaxy clusters is not a lot, actually, we're going to use an emulator, which is basically a very fancy interpolator that's going to take these profiles, and it's going to learn from them. And I can ask this interpolator then, OK, I want actually a galaxy cluster profile, or a mean galaxy cluster profile for a universe with these parameters. And it's going to give me an average galaxy cluster profile for a galaxy cluster that lives in a certain universe with certain values for the parameters that I'm giving it. Is this more or less clear? Yes? OK. Right. This is also open source, by the way. So and it's made with Python. Good. So in the end, what we have is a set of stacked or average galaxy cluster profiles. And this is going to be our input data. The network, we chose a moment-unit network. So basically, as I said, it receives a one-dimensional vector with the radial properties of the cluster. And then it will predict the mean and the uncertainty of each of the 28 parameters of the universe where this cluster lives in. Right? It's called moment-unit network because it basically calculates the first 2 moments of the posterior distribution. You see here, this is the loss function. You're calculating there the mean, and there in the second term, the standard deviation, basically. And a bit about the architecture, the hyperparameters, and the training. So basically, we use fully connected blocks. We had linear layers, a leaky relative slope 0.2, some dropouts, and then we ended with some fully connected layer. The hyperparameters, we optimized them using Optuna, which basically performs Bayesian optimization. And we had around 1,000 trials, and we let it tune the layers, the number of layers, the number of neurons, the learning rate, the weight decay, and the dropout. And the training was around 1,000 epochs, and we used early stopping to keep really the lowest validation ever model, basically. And the splits, the typical 70, 15, 15 for training, validation, and testing. Good. So let's go to the results. I mean, the results were very positively surprising. What you're seeing here in the plot, you're seeing the prediction in the y-axis and in the real value in the x-axis. And those are different, the 28 parameters, basically. And what you see here is that most of the predictions lie actually in the one-to-one line, which is very, very positive. If you remember at the beginning, I told you with the previous studies, we were only able to infer this parameter here, and now we're suddenly able to infer the 28 of them. And with a correlation coefficient which is quite high, above 0.9 for all of the parameters, and above 0.97 for the cosmological ones. So that was super exciting to actually see this. It was also something that I didn't expect. I was expecting something more modest. I was super happy about this. We did also some saturation studies, seeing where data saturates, and we found that with 30,000 space locations, already we have a completely saturated network, like more data doesn't bring anything. Now, before getting too excited, we wanted to test if there was maybe some data leakage that was ruining our experiment somehow, right? If you get such good results, it's like the first thing that you should actually check. So to rule that out, we did 3 different tests. The first one, well, the first and the second one are starvation tests. So basically, if you need to infer 28 parameters, you need at least 28 input values, right? It's not possible to actually infer with less data than that. So we try to starve it and say, okay, we give it 25 numbers as a one-dimensional vector, and we see if it's actually able to infer the parameters. And you see that here, again, the correlation coefficient here, and these are different parameters. The gray would be the regular results, and test A is the red lines here. And you see that the moment where we have a couple of numbers less as input value, this network is just not possible. It's not possible for the network to actually infer the parameters. We brought this farther and starved it more using only 5 inputs, and it went even worse. And then we also corrupted data in another test where we added random noise and saw how it performed. And we also saw that actually the signal was completely disrupted, and the information was not being extracted at all. So it looked good. That's nice. I mean, it's great. But actually, our ultimate goal is to apply this to observations. Right? Simulations are great, but we want to really apply this to our universe for real life. And I would say observations have 2 caveats that simulations don't have. And the first one is noise. Observations are by nature noisy. Typically, astronomers quantify this with a signal-to-noise ratio. And this is something that we need to take into account somehow. So we wanted to do an initial test and kind of test how a neural network would perform in noisy conditions. And how you typically would do X-ray observations in galaxy clusters, you typically take the space or the image, and you will make a tessellation. And for each of the spins of the tessellation, you will decide on a signal-to-noise ratio that you want. And then based on that, you will observe. And in the end, you have an image with a certain signal-to-noise ratio. This is a typical way in which you would do this. And I would say a signal-to-noise between 10, like 10, I would say lower limit, it's good, and 100 is great, right? So between that, it's actually a very good observation. So we decided in order to mimic this, because we are having profiles, we added random noise to each of the bins of these profiles relative to the signal of each of the bins. And we decided to add a 10, a 20, and 30, and a 40% of Gaussian noise. So 10% would be a signal-to-noise ratio of 10, and 40, a signal-to-noise ratio of 2.5, which is extremely noisy, right? But we wanted to test it to the extreme. And what we saw, which was also quite positive, is that for some of those parameters that we care about, like omega matter, omega baryon, and H0, actually the correlation stays above 0.7 when we have a signal-to-noise ratio of 10, which is something quite plausible in observations. And if we even disrupt it larger with 40% of Gaussian noise, they hold up quite well. Like here, you're seeing the correlation coefficient. Those are the parameters. And this would be like the darker one would be 40%. The lighter one here would be at 10%. And you see that H0, it's standing quite well. Omega matter as well. So that's actually something positive. And the reason for this is actually that these parameters affect the profiles in many different ways. And it looks like H0 and omega matter, for instance, affect the profiles in places where the data is not so correlated. For instance, you can shift the profile up and down. And then if I add noise, this signal is not, the information is not disrupted. Whereas if I affect in a part of the slope and I add noise, for instance, that information would be out. Like it wouldn't be there anymore because of the noise. So this is kind of the explanation for this. And then the second caveat that observations have are actually the apertures. So typically, telescopes have a certain aperture, and sometimes we cannot really observe the full cluster, depending on the location, how far away it is, and how the signal is. So for us, what's very important to try to give a hint or an idea of where probably most of the information is. And to do this, we did several tests, and we cut the profiles in different parts, and we made the neural network infer the same parameters with different parts of the profiles. And I think this plot is quite interesting, probably the most interesting of all for me, because here you're seeing, again, the correlation coefficient, and here are the parameters. And what you're seeing here is in this light purple that you cannot see that well in the screen, I'm sorry for that. But basically, the light purple is showing you how is the inference if you just take the centers of the clusters of galaxies. And it turns out that the inference is super good. It's almost as good as if you take the full profile. It's just always a little bit below, actually. So whereas if you just take the outskirts, like if you take out the 10%, the inner 10%, you actually get the darker purple line. Let's see, which has way less information, like the correlation coefficient, it's way lower. So it looks like most of the information is in the inner regions of the galaxy cluster. And this is good for observers, because typically these inner regions are easier to observe because they have way more light, way more emission. So that's actually super good news for us. And that said, they told me time's up, but I think we're on time. So what we learned from this study is that a neural network, like a moment neural network, which is not overly complicated, can already extract cosmological information very, very well. In fact, it can infer 28 cosmological and astrophysical parameters. So that's absolutely great. The network also tells us where to look. So we learned that actually the innermost 10% of the virial radius is the most informative part of the galaxy clusters, and there is where that's what we should target in future observations. And the predictions are also quite robust against noise from 3 of the 5 parameters. So, and some of the parameters we actually care most about. So that said, thank you very much. And if you have questions, you're very welcome.
Thank you so much, Elena, for this brilliant talk. Do we have any questions from the audience?
Is it tested only on lambda CDM, standard cosmology?
Yeah. I didn't want to get into the details of this because I was like, I don't know if all the audience will be astrophysicists or cosmologists. But yeah, this is purely lambda CDM. This is not.
Is it possible to try it out with different?
Yeah. You could build simulations with neutrinos. You could build simulations with modified gravity. You could do. But then you would need a new set of simulations, right, to actually train this on.
So the model is useful only in those
this
scenarios?
One that we trained, yes. The concept itself would be useful also, but we would like to modify gravity models or own some other cosmological model. But then we would need new simulations to actually represent that parameter space, basically.
I see. Okay.
Yeah.
Thank you very much. Small question. Is it powerful enough to already make a prediction that would challenge our perception of the universe? Like, do you already find, if you run it on true data, raw data, do you already find values that do not agree with what people have measured in the past? Or?
So that's a super interesting question. I didn't do that yet, and I don't think it would work yet, because there is this, what it's called simulation to observation gap. So simulations are not a perfect representation of the universe, because then we would have solved the problem. And then to make the neural networks robust towards this gap between simulations and observations, we still need to have some work to do, basically. But that's the idea, right?
Thanks for the nice talk. Kind of building a little bit on that, and I'm sure you get this all the time, but is the next step to kind of add more observational uncertainties, not in the form of just simple Gaussian noise, but obviously calibration of galaxy cluster profiles is kind of its own can of worms.
Yeah, what I would like to do next would be to take actually images of galaxy clusters from the simulated data and try to go through the same pipeline that, for instance, EuroSciPy clusters would go, or something like like this. But for that, we need some collaboration between simulators and observers, which is always we need to enter into a dialogue there. Yeah. But yeah, that would be the next step.
Yeah. One more question, if I'm being greedy. Just in terms of your simulation, obviously you can always add more parameters. So obviously there's a lot of AGN feedback, black hole stuff, supernova stuff. Is there something in the next iteration that you guys would want to add to kind of increase the complexity of your simulation?
So
I'm done.
I mean, we had another paper out not that long ago, actually in June, where we actually modified 35 parameters that had to do with UV radiation, and some other parameters in the simulation, initial radiation, and so on, heating and stuff. But I would say that, in my opinion, going farther in more and more parameters doesn't make so much sense, because in the end, these astrophysical parameters are something artificial, right? We put them in to control the astrophysics of the simulation, but what we are interested in is actually in the cosmological model. So what I think is the next step is to try to bridge that gap between what we are not representing well in the simulations and the observations. My personal opinion, at least, on that.
Anyone else?
Technical question this time. So I'm not so familiar with the notion of mixing Gaussian optimization and simulations as you do. So when you say you have a batch size of 256, do you do, with your Gaussian optimization process, do you take the 256 points that would give you the most information? I mean, I don't know how you sample these points.
But I meant that for the moment neural network, and the batch size, it's just sampled randomly. It's not like optimized.
Okay.
What do you do? Where you do the Bayesian optimization is with the emulator.
Okay, so you don't choose the simulation parameters that would give you the most information relative to where you are in the training at this stage.
No.
Okay.
No.
Okay.
No.
We don't see any more questions, so let's thank Elena once again. Yeah, and now we'll have a couple of minutes of break. If you want to change the room, feel free to do it. If you want to stay for the next exciting talk, please do.
test now. Yes. All right, I will try to do that. I will show you. Perfect. So you hear me loud and clearly, or should I move the mic? It's good? Okay.
Okay, yeah, so let's welcome our next speaker, Stephanie, who will tell us all about scikit-learn.
So yeah, hey, I'm Stephanie. I'm a scikit-learn maintainer and an open source developer working on scikit-learn for Probable. We are going to talk about scikit-learn's metadata routing, which is a not so new feature anymore. So we are developing it in experimental mode for 3 years now, but it's maturing and like kind of almost ready. And I'm going to talk to you about what actually we mean with metadata routing, what is metadata for us, and what you can do with that, how you can apply it on your own, and about the most recent developments. So starting with what do we mean with metadata? So basically, it can be anything. So this is a very potent and flexible API that we have now there in scikit-learn. So it can be, so you can think of it as data or any kind of information, basically, that you can apply on top of your tabular data. Or something to pass into a function, your function maybe, besides x and y. Use cases are mostly to make your model better. It's not about having a better score, but having a more realistic model. You can use it in fairness-related context, in your business logic, or some other custom behavior. And with routing, we just mean the mechanism behind passing metadata to the correct, to the place where it's actually used or consumed. So what is the difference about having metadata routing enabled or not? So if it's not enabled, this is a default. So if you don't set any configuration, you don't have it enabled. So what it is sometimes, so metadata that we have in scikit-learn is mostly sample weights and groups. So you can use both of these extra params metadata in a very restricted way. So you can pass them directly into your metric or directly into fit. But the problem is when you try to actually pass sample weight or groups across different levels of nessedness. For instance, you call a fit method of an estimator that knows how to handle sample weight, but you call it inside a pipeline, you actually weren't able to pass sample weight into that pipeline. So when you enable metadata routing in scikit-learn, a few nice things happen. So you can pass sample weight and groups in all kinds of nested structures. And you can also use metadata from other libraries and pass them around to the right space. So this means with metadata routing, scikit-learn is much better integrated with other libraries that you might want to use or combine. And you can also define your custom metadata and do whatever you like with that. All right, so I will show you how it works on a little example. So let's imagine this is data this is a medical question of whether a certain new treatment, let's say a certain new drug, is actually reducing the recovery time. So we want to predict recovery time, and we have this messy data set that is from real-world observations. So there can be several problems with a data set like that. So first problem is this data might come from different sources. So in this case, it's different hospitals. So the icons on the left are the different hospitals. Every line, every sample is a patient.
So we know that hospitals are different, so they might have different kind of medical devices available. It's a different kind of patients, so they might have a different socioeconomic status. So they might be in different cities or in different countries, and all of that influences the data that can come from these hospitals. So another problem with this kind of data could be that within the features, the distribution is not representing the distribution that you want to predict for. So it could be, for instance, that this treatment is mostly for older patients because it's a disease that mostly older people get. But then in your data, you find out the younger people are over proportionally presented. So these kind of biases can be introduced by just real-world observation data. And now we get to groups and sample weight and how these can actually try to navigate this or try to make up in a way. So let's first talk about groups. Groups is something so let's go back one slide first. So we have these hospitals, they are in different groups. We still actually want to predict on the whole data set, but somehow take these different origins of the data into account. Then we can use groups to actually pass groups as separate data, but we don't want to anyhow combine it with our X data set, but we just want to actually, when we train a model and when we cross-validate it to find out if it's actually stable, then we want to pass groups to the splitter so it knows actually it can handle them differently. So this is what happens when in scikit-learn you use the group k-fold splitter. There are two group splitters that we have. These take group into account, and you also have to pass them. So it's the same thing as k-fold. But the group k-fold does something on top. It tries to, no, it doesn't try to, it does. It does never train and validate on the same data, because otherwise we could introduce data leakage. So there are some structures in the data that we actually don't want to predict on. If a hospital comes from a poorer area and there are poorer people in this hospital, we don't want this kind of information somehow in the validation process. So hospitals or like data that is on the training set will never be validated on, and vice versa. Okay, and this is something that we had always been able to do in scikit-learn, even before metadata routing, but I'm just demonstrating it to you for the next step. So if we, let's see. Nah, that's even worse. Okay. I will just tell you then. So let's say we want to use rich as an estimator, and we want to cross-validate on it, and we want to use a group splitter. We can just pass groups into cross-validate, and cross-validate knows that it should be passed to grouped k-fold. But this is a hard-coded thing, and this was possible before because we know that grouped k-fold always needs groups, because otherwise it would not work. That's different for other metadata that you maybe can pass or cannot pass. So we go to the sample weights example. So using sample weights metadata in scikit-learn is a bit, the structure is similar, but the question of actually when you use it is to rebalance somehow your data. So going back to the example with the older and younger patients, and we actually want to, so actually we don't have as many older patients in the data set as we would actually want to predict on. then to fit on, then actually we can use sample weight to resample, kind of, and there are methods of how to how you compute the sample weight in this case. So when a sample, let's say, would have a sample weight of 2, this is for the training as if it would be like the same data would be there twice. This means like for the training error, it would reduce more on those samples with a higher sample weight. Okay, when we want to use it, the same way as we used groups, we have a problem without metadata routing because it just throws a type error. So we can't just pass sample weight into cross-validate and hope that it's going to be used in rich.fit. Rich.fit would actually understand it, but cross-validate doesn't know what to do with that. And the same kind of thing would happen if we would combine these two. It's actually the same error that we see here, but just for the sake of where we want to go and the next code example, I have combined it here already so you can see. So we have our rich estimator again. We know rich.fit can consume sample weight. We define our own scorer that can also consume sample weight, and we know group k-fold takes groups. So when we now want to grid search on rich and then cross-validate everything, we get the same error as before, but with metadata routing enabled, it would work just fine. I show you in the next slide. So this is the same code with the comments removed, and now we build up what we need to do for metadata routing. So there are 3 steps. So the first one is you have to enable the metadata routing because, as said, it's experimental still and it's not enabled by default. You can get odd errors if you don't disable it afterwards, but we also have a context manager for that. You can also use this one. And then you pass metadata to the top level tool. So the main idea about metadata routing is that you don't need to, that you have a top level tool which is the outer level of actually that you want to address, that you run and then it runs all the other stuff. There you pass your metadata. And this can be a function like cross-validate, cross-val score, and so on, or it can be a meta-estimator. A meta-estimator is every estimator that takes an estimator as an argument. There are like 50 or so in scikit-learn. And then the last step is you need to set requests. So we internally call these things set method request methods, which is kind of a funny name, but this is because there are so many of them. So there is set fit request, set score request, set transform request, set fit transform request. Wherever you want to actually use your metadata in, this is where you set the request. And you have to set the request everywhere where this metadata that you pass below here in cross-validate could be used. So scikit-learn detects where it can be used, and then you need to decide. So you need to set it to either true or false. Otherwise, you will get an error that leads you to actually set the requests. Okay, in this case, we want to route sample weight to fit, enrich, and to the scorer. So we set it to true, and then that's already it. So this is everything you need to do. All right. Then after metadata routing has been introduced in scikit-learn, we found out that, actually, for us even, it's not only groups and sample weight that we can do. Actually, we can solve a lot of other problems that we didn't know how to solve before. So, for instance, in this case, where an estimator internally splits off a validation set and then does something with this. So we have his gradient boosting and some others that do this internally, and they would use it to determine early stopping. This was fine to do it like automatically randomized inside before, but there was also the data leakage problem whenever you wanted to use his gradient boosting or others in a pipeline or in some other nested structure. Because when you have transformers before, so you should split off the validation set early on. And only split it off for fit and predict. But basically, you should do it early on, and if not, there's a data leakage problem. And now, with metadata routing, we could actually solve this problem. So for pipelines that usually have some transformers, and then in the end, some estimator that would be able to fit and predict, there is a new param called transform input. And this one would actually, it defines which metadata, which other data next to X would be transformed during the whole process. So users can do train test split early on and then pass X val, so the validation set, into the pipeline, and then it gets transformed alongside. Yes, LightGBM is compatible with this for a few months now, and XGBoost not yet, but probably to come. I will also show you how that looks in code. So here again, of course, we set in metadata routing to true. Then we set the request. So and now let me explain the code first. So we have some data, and we do a train test split early on. And then we have his gradient boosting classifier defined, and it can fit with early stopping true, meaning yeah, it stops early. So when we set the fit request, we can also pass xval and yval as metadata. So it can take this into account compared to as before doing an internal randomized split. So when we put the his gradient boosting classifier into the pipeline and have some transformer like a standard scalar before, then we pass also transform input, and we define the name of the metadata that should be transformed alongside X as a string. So in this case, it's called xval. And then when we run the fit on the pipeline, it's, yeah, it would transform xval up until the point that it is consumed or used. Okay. So, yeah, I actually have explained this here as well. So, all right. Good. Then little outlook, or what are we recently working on in this area? So a similar problem as in the pipeline we had discovered in target encoder, which does an internal cross-fitting. And it couldn't do so for groups because it was also internally determined which kind of splitter is going to be used. But now you can actually pass a splitter that accepts groups and also pass the groups alongside. So that is something that we fixed. That is now like enhanced functionality. And currently we are working on using metadata routing inside callbacks. Callbacks is something that was just introduced a few months ago in the 9.1 release. 1.9. And one of the callbacks we have there is a scoring monitor. This one just returns the scores at different times of the training, like also in between loops. And it would be great to actually see how a validation set does on the scores and monitor them. So we are working on introducing metadata routing into the callbacks, so you can see then everything, and there will also be an early stopping callback, so that one will also use that. If you are a third-party developer or do your own custom estimators, then it will be very much easier to integrate metadata routing in it soon because we are working on a developer API for that. We are also working on default requests, meaning that pretty soon, I can't promise, but hopefully soon, you can set, you don't need to set all the requests. The set request method requests you don't need to do if you leave the defaults because we do it for you and you would only change it if you want something else. Yes, and there are some visualization and debugging tools to come. Okay, so that's it, I think. I was faster than expected, but then we have more time for questions. I will share the slides in the Discord for the room afterwards. There are some sources, you can click on them if you have the slides, and then thank you for your attention. And then happy to take your questions.
Yeah. Thank you, Stephanie, for this talk. Do we have any questions from the audience?
Maybe that's a dummy question, but what do you mean by callbacks in that? This is the standard for like C, C++ asynchronous idea of callbacks in slots? No, this is not for asynchronous programming, right?
So this is something that is invoked while some other function runs. So we integrate callbacks into fit. And
so yeah, this is asynchronous programming way. I mean, for asynchronous programming, when something's run and you set a callback to be
it's the same
triggered.
thing. It's the same thing. And then we try to find out actually what users want. You can participate in the discussion. So right now we have a callback that shows progress, so progress bars during training, and the scoring monitor, and we want to have a early stopping one. There are some other ideas going around, but you're happy to actually find the issue and say what you want and what you need.
Okay, so this is because you cannot use async.io or async.io for asynchronous programming. You can work on coroutines.
No, it's not needed. We have different threads for it, and it's fine since you know when to use a callback, and they are very light.
In that sense, okay.
Yes, they're extremely light. They don't add
I see.
too much computation.
Okay.
At least the ones that we have right now.
I see. Thanks.
Thanks for the clear explanation. I like it a lot. I was wondering, so the syntax is pretty awkward, at least for me as a developer. Can you maybe say something about how backwards compatibility restricted you or the team in choosing how to set this up?
That is a very long-running thing, and I haven't been around in the beginnings, so that's like probably 10 years old. So I guess I can't take this question, but yeah. I mean, I think, so when we look into the future, actually the syntax, so I don't think that the syntax is any way related to backward compatibility, because when we set default requests and when we set when we enable it by default at one point, then there will be nothing different than now. So
maybe, for example, the class structure will dictate how you can do the a request parameters, right? Yeah. I mean, yeah. So my talk will be about providing a similar way of programming it under the hood. So that's why I'm saying it. But it's a no way suggestion. I believe that it's not possible to apply that here because you have a certain structure that by breaking that, the users will not be able to use it at that point, right? So then you have to abandon the classes, for instance.
Depends on what you mean. But we do an internal restructure of this module, but I mean, what you see outside will be easier anyway. So I think that's good then. So it won't interfere with your programming a lot. So if you don't need to set the requests because they're automated, then everything is as usual.
Yeah. Let me take it offline.
Yeah, okay.
Thanks.
Okay, any more questions?
One question, but so if you go back to the example, you were having two arrays of data. So one was group, one was sample weight. Now, in the case of group, that's something that is not recognized by every kind of estimator, but sample weights is a pretty standard thing in scikit-learn. So the question is, why do you require the user to manually request the sample weights if it is a built-in that is supported in pretty much everywhere?
Right now, we wanted to have flexibility for the users, and when we were developing it, it wasn't so clear actually where users want to route sample weight to and where not. So these are then also statistical questions, and this is like software engineering work. So the users are free to actually route sample weight to where they want and not. So in order to do this, they need to be able to actually say, here I want to route sample weight to, and here I don't want to do it.
But is there a use case for having the weights and then dropping them in some steps, but not all of them? I guess it's probably not so common.
I'm not sure.
Okay, thank you.
Hi. My question is about the transforming validation set use case that you showed. Yeah. So without the metadata API, how would it look differently? Is it that the standard scalar operation would have been done outside of the pipeline or some?
I mean, it would make it very complicated to users, actually impossible, I think.
Yeah.
So there would just be data leakage. And we didn't document it to users even, so there was some, you can call it a bug that nobody noticed and nobody knew of. So you would just pass X down the pipeline, and then internally you'd say early stopping, yes, and internally it would do it, and you wouldn't even notice it.
Right. Okay.
Okay, that's all?
Thank you once again for this excellent talk. Thanks everyone for participating. Let's thank our speaker again. And now we have a coffee break.
Thanks.
Anyone know how we turn this thing on? The HDMI cable also, I'll note, no longer has a cover. Yeah, that's the problem with sitting in the front. Okay. Let's see. Yeah, yeah, yeah. Yeah. Nice. Okay. Hi. Just two. Yeah. Yeah. Is that me? Is that me? Okay, there's some feedback. Oh, wow. Oh, wow. I guess it's because I got this big power bank. Let's see the power bank. No, it's just the phone. That's troubling. That means there's something coming out of the phone. That's amazing.
Hello, everyone. Welcome to the next session. And next we have Bryce. We already heard one of his talk. And this is the second one, which he will talk on profiling GPU codes. So the floor is yours.
Hello. So, hi, everyone. I am Bryce Adelson-Lelbach. I'm a principal engineer at NVIDIA, where I am responsible for programming language design and evolution. I work in the compiler org at NVIDIA. And today I'm going to show you some of the tools for profiling GPU code that I use every day. As scientific Python programmers, many of you are probably using GPUs, but often that may be indirectly through frameworks and libraries. And even if you're not writing the GPU algorithms yourselves, it's a good idea to know how to identify problems, or at least identify the general area where there are problems. So I'm not going to cover many of the details of like how to write GPU code today, et cetera. We're going to kind of gloss over that and really focus on the profilers. However, we have a great great collection of open source learning materials on our Accelerated Computing Hub GitHub repo, including Jupyter notebooks for all of the demos that I'm showing you here today. And you can run those either locally in a container, or you can run them on Google Colab, or you can run them on our Brev developer cloud platform. And all the profilers are actually like in the Jupyter notebook. I'll show you some of that later. There's a lot of other material there to learn about how to write GPU code and how GPUs work. So we're going to use two different profilers today, Insight Systems and Insight Compute. Insight Systems is a tracing system-wide profiler. So it gives you an eagle-eyes view of everything that is happening in your code. That's both CPU and GPU. It's actually a great profiler to use just for CPU code too. Not what we're going to talk about today though. It takes snapshots of your program during its execution, and it builds up a timeline of your entire program's execution. It helps you visualize the phases of your application and identify bottlenecks, hotspots, and idle regions. And it has a relatively low overhead, so it's almost always the tool that you should start with when you're looking into a performance problem. Insight Compute is a lot more targeted. It is a kernel profiler. It is meant for deep dives on the performance of a particular hotspot and a particular piece of code that is running on the GPU. So it only looks at GPU stuff. Insight Compute collects detailed information from hardware performance counters, stuff like cache information, instruction, stall information, things like that. Now, to collect all of this information, it must run your program many times. The ways that the hardware performance counters work, there's a bunch of instrumentation in hardware that collects all of these metrics right next to the core. So it's very accurate and detailed. However, there's only a few lines out of the core for this information to travel. And so at any given time, you can only have a couple of these hardware counters enabled. If there were more lines, then they wouldn't be able to get it would interfere with performance, it would interfere with the design of the chip. And so what happens is Insight Compute will actually run your code many, many times. In the examples we're going to see, it'll do 44 passes. And so if you can imagine, that can make your code run a good bit slower sometimes. It's not always exactly 44 times as slow because it'll run some in parallel, but it is a very heavyweight thing. It's something that you want to run in a small targeted piece of your code, not your whole application. So now we'll jump over to a Jupyter Notebook. So we're going to look at Insight Systems first, and time permitting, we'll look into Insight Compute. So first, we're going to look into this simple little application that uses CuPy. Short version of what CuPy is. Yeah, I can do that. So CuPy is like NumPy, except the things run on the GPU. That's all we really need to know about it for right now. So we're going to look at a code that estimates the dominant eigenvalue of a matrix using the power iteration algorithm. This is not a very efficient algorithm for doing so, but it is very simple. So it's an iterative method that uses a bunch of matrix multiplications. So first we do this matrix vector multiply, and then we do this eigenvalue estimation with some matmuls. And then we have this residual calculation. And the way that we're going to run this, we're going to scroll down here. This is our little configuration for the simulator. So we're going to give it a maximum number of steps, but we won't necessarily run for those steps because we will also give it a residual threshold. And once the residual threshold is below this like cap, then we'll say the run's terminated and is converged. Or if we don't hit that before we hit max steps, then we run until max steps. We also won't be computing the residual every step. We're only going to do it every 10 steps. And every 10 steps, we're going to do that check, see if we've converged, and we will also do output. We'll save a checkpoint every 10 steps. So this is meant to sort of be representative of what a lot of iterative solvers look like in practice. And then we also, this is just the matrix size. We're going to work with a square matrix. And dominance is just how much larger the top eigenvalue is. This controls convergence, so higher equals faster. We're not going to really play around with this much. We're not going to look at this. This is just the code that generates the matrix. It's just like it uses that dominance parameter it generates a random matrix, and it uses that dominance parameter to make sure that one of the eigenvalues is greater than the other. And then here is what the code looks like. So first of all, we're going to initialize our solution vector. It's just going to set it to 1s to start. And then here's the solver. And let me let me switch back here to show you guys the diagram. So we're going to have two for loops here. We got an outer for loop that is the loop over groups of steps, because we want to do this residual check and this output every n steps. So that's going to be a for loop where it's going up until the maximum steps with a step size of the output frequency. And then within that outer loop, what we're going to do each iteration is first we do the special step where we both compute the solution and we compute the residual. And then we're going to check the residual and we're going to do our output. And then we will do the other 9 steps where we're just purely doing compute. So 2 loops should be fairly straightforward. All right. So this is what the code looks like. So here's where we're doing the computation of that one special step and the residual here. And then this is where we're doing the check, where we're doing some IO here. We're just printing like status, you know. And then here we're saving the checkpoint. And then here we're doing the convergence check. And then right here we're running those other 9 steps. Very simple code. The CuPy version of this code, just replace NP with CP. That's it. Boom. Code runs in the GPU. OK. So now let's go ahead and look at a profile trace. So where is Infinite Systems? So this is the profile trace that we get out of running that. The notebook itself has the little command to run it. There's a little, conveniently for Jupyter Notebooks, we have a little cell magic that you can put on a cell. You can put %% insys at the top of a cell with this plugin that we have, and then it'll just profile that cell. Very convenient if you're using Jupyter Notebooks. So we look at this, and, well, is this useful information? Like, there's a lot of, like, scary words and terms. We can't really see anything. One thing that we should note right away, this is supposed to be an iterative solver. And if we look at this, there's not a lot of, like, we should see a recurring pattern here. The next thing we might note is that the biggest thing, the only like 2 pieces of text that show up fully is Q module load data twice. So we don't know what Q module load data is. But if we use our critical thinking and reason a little bit, that sounds like that's like loading module data. So that's probably some form of initialization. What it is that's actually loading the code. So this is where it's loading the code. You can see there's a DL open here. So all of this is like not very interesting. I mean, maybe immediately one takeaway is like, wow, it seems like we're spending a long time on initialization. But that's just because the solver is running for a very short time, because we wanted it to be short enough to be able to like get a benchmark trace and not take forever. If we ran it for a lot longer, it would be less interesting. So the only stuff that's interesting to us is actually the stuff right over here. And if you look right over here, this kind of looks like this might be an iterative pattern. So if you've ever used like a music editor or video editor before, this UI is very similar to that. It's got tracks over here. You can expand some of the tracks. You can collapse some of the tracks. Now, I personally think that the naming of some of this is a little confusing. The one that says CPU is what's happening, is like the frequency and utilization of your CPU cores. The one that says CUDA hardware is showing what stuff is running on the GPU. And the one that says threads is showing what stuff is running on the CPU. I personally find that a little confusing. We'll show you another tool that makes it a little bit less confusing in a second. So there's a few things I can do here. First of all, I can select a region here, like this region, and then I can right-click on this, and I can filter and zoom in. And so that's going to bring me right into this region here. And this is looking more like what we would expect to see. We're seeing a recurring pattern here. Because this is a 30-minute slot, right? But this was swapped with the other talk earlier. I'm going to keep going until the break. OK, so if we start looking here, the other thing you can do, I can just click on a particular call, and I can I can do fit to screen and go into that particular call here. And now I'm like zoomed into like millisecond time range, like a very short time range here. But if we zoom out here, we still don't have like super useful information. Like we can clearly tell that this is like, the iterative steps that we want, but like we don't know what's going on. So there's a few things we can do to make this trace a lot more useful. So we go down to here, and we're gonna go here. There's two different things we should do here. First of all, let's see if I can find it. So first of all, we can limit what part of the code we are profiling. By default, these tools will profile your whole application. But if you pass these flags here, then they will only profile the region that you control. So instead of starting when the program starts, they'll start when you start it. And there's this very useful little thing called, that you can find in CuPy. PyTorch has some equivalent version of it, but for this community, you probably want to use the CuPy version. It's called cupyx.profiler.profile. It's a Python context manager. And if you just use it like this in a with statement, and then everything in that with statement is in the profile. And everything outside of that is not going to be profiled. If you just do this and you don't do the flags, it's not going to do anything. So you got to do the flags too. The other thing we can do is we can use this library called NVTX. NVTX will add annotations to your code. They have zero cost. They won't do anything. But when you run it under the profiler, those regions will show up as specific regions with a specific name that you've given them in the code. And again, this is just a context manager, and you can just pass it a string. You can pass it a format string too. It's very nice and convenient and easy to use. So these are the two things that I recommend you do. And again, both of these things, they don't really have a cost in your code. There is some cost on the Python side in that they are like creating a Python object, but it's not, if you're not running in the profiler, it's not doing anything. So what I've done is I've gone and added some annotations to this code. So I added one, and you can nest these annotations too, which is very nice. You can also give them colors. And there's a few other things. You can give them categories. So I've added one annotation here for the outer loop, calling it step I to I plus 10. Then I've added an annotation for that compute and residual region for step I. And then I've split the next part, where we were doing the residual and the convergence check. I've split it into two steps, one copy and one IO. In this copy step, we are now explicitly copying this stuff from the GPU to the CPU, because previously we were just sort of lying, we were implicitly doing that. Things like this if check, things like printing, all that's going to happen on the CPU. And then finally, we have a with around the compute I plus 1 to 10 steps, and then another nested one for each one of those individual steps. So now I will show you the other way you can do these traces, which if you use my I have this little package called Insightful that you can use within a Jupyter Notebook, and then it gives you this nice little button. You press this button, and it opens it up in this thing called Perfetto, which is the Google Chrome trace viewer. It asks you if you want to trust the thing. Yes, you want to trust the thing. I'm a very trustworthy person. And it'll pull this up. And this is what it looks like here. Let me zoom this out. And now we can open these up. And these, the way I've set this up, it's a lot clearer. There's just two bands. There's host, there's device. It's very simple. And navigating in Perfetto, you can use the W, A, S, and D keys to W and S zoom in and out. A and D go left and right. The search thing's also useful. Let's search for like step 30. This gives us step 30, and now we can like zoom in there. Okay, so now we've got like some information that actually is maybe useful. Now we can see what phases are happening where on the CPU and the GPU. So some of these phases appear in both places. Let's look at like the compute 16. Maybe this, I showed you the version, the step count here. I was saying 10, but I think the notebook was using 15, and I was looking at an older version of the notebook. So compute 16 to 30, you'll notice if I make a little box here, you'll notice that clearly this region, compute 16 to 30, starts on the CPU before it starts on the GPU. And the reason, of course, is that we launched the work from the CPU onto the GPU. And so it takes some time, about this much time, to go from the CPU to the GPU. We call that launch latency. And so it's useful to actually look at the regions on both places. So other stuff we can notice here. So first of all, if we look at our GPU, let's forget about the CPU for now. What's happening here? Well, at this point, we're in the loop, we're in the step, but we're not doing any compute. We're not doing anything on the GPU, right? So there's these gaps where nothing's running on the GPU. And during those gaps, what are we doing on the CPU? Well, we're doing I/O. So let's take another look at the code here. So, okay, this is what I showed you, but this is like the algorithm if we wrote it in NumPy. But in reality, it's actually more like this, because some parts of this run on the CPU and some parts of this run on the GPU. And the issue is that when we're doing compute on the GPU, we're not doing anything on the CPU. When we're doing our I/O on the CPU, we're not doing anything on the GPU. So we're underutilizing both processors. Now, what we can do is we can do these things at the same time. We can add some asynchrony. So what we can do is we can copy the residual in the solution vector from the GPU to a buffer on the CPU. And then we can start outputting that residual on the CPU once the copy finishes. And the compute of the next n steps can begin at the same time. The compute and the output both just depend on the residual in the solution from the last step. And once we have that, we can do those two things in parallel. So let's take a look at what happens if we go and do that. I'll show you what the code actually looks like. So I showed you before that we had these CuPy.asNumPy, which is the way that you spell a copy from the GPU. Oh, okay. So CuPy is a slightly older library. It would have made sense to have had a function like copy or transfer from GPU to CPU. There's like 3 different ways to spell this in CuPy. None of them are good names. There's .git. I don't know what that does. I think this is the best one. AsNumPy takes it from the GPU, gives it to me on the CPU. AsArray takes it from the CPU, gives it to me on the GPU. So these are the copies that we were doing before. And what we want to do is we want to make these copies asynchronous. And then we want to make sure that we don't start the I/O until those copies have finished. But we can start the compute as soon as those copies finish. So we want both of these 2 steps to depend on it. So we go down here. All of these GPU operations, all this math, everything here, these are all asynchronously launched on the GPU, and they will all happen in the order that they appear. So we don't have to do anything to make the compute here happen after these copies. That will just naturally happen. But what we do need to do is we need a way to move the I/O down and then to have this I/O wait for these copies to finish. We've now made these copies asynchronous by marking them as blocking equals false. And then what we do is right after that, we record an event, which we call copy event. This puts a little marker, and then later we can go and synchronize on that marker. We do that right before we do the output and everything else. But before we do that synchronization, we launch the rest of the compute. And so this means that this compute is now running, this whole step is now running at the same time as this I/O. So let's take a look at what it looks like now, which is this thing? No, that's the one that doesn't have stuff. Okay, we're going to be over here. Okay. So if we scroll back in, now we can see that it looks a lot better. These little red things here, these are the actual kernels, and they're running pretty much the entire time. If you ran this on a slightly different GPU, or you ran this with like fewer steps, you might still see a gap there. Because you have to, in this case, if you wanted to fully utilize both processors, you would pick your output frequency depending on like the ratio of how long the I/O took versus how long the compute takes. I've just happened to balance it perfectly here. A couple other things to note here. In this first one, you saw this CUDA memcopy async that it appears that it takes a really, really long time, which is confusing for something that's an async. That's a little bit like falsely attributed here. What this really represents is not how long the copy takes. It really represents the length of the copy and then the synchronization, waiting for that copy to complete, which is what we were doing in the first one and which we're again doing here. That's this step right here. So there is still some period where we've actually got more compute here, like if I/O finishes faster than the compute. So we could maybe get rid of a few of these compute steps and output a little more frequently. And what time is the break? Okay. Okay, so now I will go on to the next one. Okay, so let's look at Insight Compute a little bit. So, can we see this now? Okay, so I'm going to talk a little bit about Numba CUDA, and we're going to write a very simple kernel, and then look at how we can profile that in Insight Compute. So the main way that you write GPU kernels in CUDA Python today is with Numba CUDA. I gave a talk about it at EuroPython. If you want, you can go watch it. I think they already have the videos up. Very cool. Numba is the JIT compiler framework for Python. It takes Python AST and it lowers it down to native code. It does this by lowering it down to an internal IR, then does type inference, figure out all the types, and then does some other transformations upon it. This is like not, when it runs, it's like not real Python code. There's no interpreter, there's no reference counting, there's no Python object semantics. It's just like it's as if you wrote C code, but with nice Python syntax. So it's important to understand that it's Python syntax, different semantics, C++ object model under the hood here. Okay, so what exactly is a GPU kernel? It's just a function that is run by many threads at the same time. So we'll write a simple one. It's just going to copy elements between two arrays. So with Numba CUDA, you use this CUDA.jit thing to indicate that a function is going to be a kernel. The inputs to our kernel here are just going to be two NumPy arrays. And then the first thing that we do in the body is we need to figure out what piece of work we're going to do, which element is this thread going to copy. So we can use this function CUDA.grid to get a unique index for each thread. And then we're just going to copy one element from the source to the destination. Now, if we have 8 threads, for example, then we'd copy 8 elements like this. Now, on GPUs, threads are grouped together into a hierarchy. The lowest level of that hierarchy is called a warp of threads. All of the threads in a warp execute the same instruction together at the same time. Some of the threads may be inactive during the execution of a particular instruction, but they aren't doing something else. They're still executing with the warp. Threads in a warp can communicate with each other with a variety of different fast synchronization primitives. And then those warps are grouped together into what are called thread blocks. And all of the warps in a block run at the same time, but each warp may be executing different code. So blocks can synchronize with each other, and they can communicate with each other too. And that's the main level of the hierarchy that we deal with. So this kernel is not, and in the way that you launch these things, they have like a special syntax in Numba where you use the square brackets here. And you have to tell it when you launch it the number of blocks. It's going to be 2 in this case. And then also the number of threads in each block, which would be 4 here. Now this kernel copied just 1 element per thread, which is not very useful for a variety of reasons. You don't want the number of threads to be tied to the size of the input element. So we'll write a slightly different one here. So this time we're going to copy multiple items per thread. This time we need to multiply our thread index by the number of items to account for all the extra items that all other threads will have handled. And then we'll have a simple for loop that would copy all of our items. Then when we launch our kernel, we have to just do some math to figure out how many blocks to launch. So let's look at how this kernel will access memory. So here's a table showing what a grid of 4 threads will access. So thread 0 would access items at index 0, 1, then 2, etc. And that should look really good, right? Because we're moving through memory contiguously without any stride. And an optimizing compiler would reorder the loads and stores, grouping them together, and then they could be combined into vectorized operations. And even if this code isn't vectorized, it'll still have good memory locality. And all that's true on CPUs, but GPUs work a bit differently. To understand that, let's now take a look at a profile for this. So I got another notebook here. We got our memcopy kernel, looks like this one here, the same thing I just showed you more or less. For Insight Compute, we can run instead of having that Perfetto thing, because Insight Compute doesn't show you a timeline, it just shows you like little facts about your program. And I have a little Jupyter widget that shows us all those facts here, which is pretty helpful, but the Insight GUI is nicer, so we're going to look at it in the Insight GUI. And we could do that in, well, not there because my internet seems to have died, but we will pull up the trace here in Insight Compute. So when we open something up in Insight Compute, this first page here will show you a summary. And it has all of these things that they call rules. And these are like various patterns, like performance issues that it may have detected in your code based on some pattern matching engine. It's usually actually pretty good at this. Now, a lot of these use a bunch of big, scary words. So you just sort of have to like infer what the useful parts are. So we see that there's 3 here. So we see this thing that says about uncoalesced global accesses. That's a big, scary word. This workload has uncoalesced global accesses, resulting in excess sectors. Don't know what excess sectors are. 75% of total of, I don't know, X sectors, whatever that means. It says check the L2 theoretical sectors. Aha, L2. So something to do with memory, okay? Something to do with memory, particular with performance in the cache. And this is how you should sort of read these things. Is like there's lots of big and scary words. You don't have to understand all the words. What you can take away from this is it's telling you that there's some memory access pattern that is causing bad cache behavior. We don't know yet what all the details of that are. If we look at the other 2 hints here, it's also like this says something about access pattern, something about access pattern, global load access pattern. It's all talking about access patterns, and it keeps referring to uncoalesced accesses. And the second one here, it says something about on average 8 of the 32 bytes transmitted per sector are utilized by each thread. And it says this applies to 99% of the sectors missed in the L1 cache. So that's an interesting fact. So we don't know what L1 text means, but if you read this like from context, L1 is the first level of caching, and 99% of the time there are misses in it. That's not good. So if you go to details, there's a bunch of metrics and charts and other things here. And in particular, there's this great thing that's called the memory workload analysis chart. And there's a bunch of other charts and graphs here that are useful. This is my favorite feature of Insight Compute. So this shows you the whole memory subsystem of the GPU and how your data moves through the memory subsystem of the GPU. I neglected to mention this earlier, but in this benchmark, we're copying 2 gigabytes of memory from somewhere to somewhere else. So when we look at this, it'll show you main memory here on the right, all the way over to registers and your kernel here on the left. And data flows from the right to the caches all the way over to the left. You'll notice here that you've got this L1 hit rate that is pretty abysmal. How are we? What time is the next session? Okay. All right. I'll wrap up in 5 minutes. Okay. Okay. So the L1 hit rate is pretty bad here. You'll also notice that it's like, look at how much data we're moving. So we've got 9 gigabytes of data that's moving between the L2 and the L1 cache. We're only copying 2 gigabytes. So this indicates that there's a lot of waste due to like misses here, where there's also a lot of transfer between device memory and L2 memory. So if you go and this sort of would give you the right clues to point you to what the true problem here. And the problem is, that comes back up, how we're accessing memory. So what we were doing is we were loading contiguous chunks of memory. Now, this is what's called blocked arrangement. This is not actually what you want to do on a GPU. You want to actually load strided memory like this per thread. And when we remember that thing I said earlier about the warps executing instructions at the same time, all the threads in a warp execute the same instruction at the same time, then this makes a little more sense. If you think about this from the GPU direction, you're really executing this load in lockstep. And so in the previous version, you were doing loading from 0, 4, and 8, and 12, et cetera. So that's a contiguous load, not a strided load. So what you want to do is you want to change to this memory access pattern. If you want to check out more about this, you can go and see the tutorial that is on GitHub. And hopefully this was informative for everyone.
Thank you, Bryce, Thank you for the talk, and apologies for all the confusion. The session is open for questions. We can have one question at max. Yeah, or we can move it to the coffee sessions. I see there is no more questions, so let's start. Okay.
Yes, so I wanted to ask, because from what I know, Numba CUDA was developed also by NVIDIA, or at least contributed to. And my question is it still seen as the primary library for using CUDA in Python? Or are you gearing more towards Qtile, or, for example, stuff from other companies like JAX or Triton?
It's actually, I think it's on the GitHub. It's not officially. You guys see it. All right, folks. I'll be at the,
So thank the speaker once again, and we will meet at 4.
I just don't know why they. And then he was also not stopping. Yeah, I think he also confused the timings. Yeah, but. Sorry for the delay.
I think we'll have 5 minutes to set things up for you. So yours will be 30 minutes for sure. Yours will be 30 minutes. Because there was this confusion for the last one.
So I think in schedule it's 30-minute talk, right? So do you want to like a 5-minute Q&A buffer?
Yeah, so it will be like 25 minutes talk and questions.
Okay.
I will give you a notice on 5 minutes left for talking and 2 minutes and 1 minute.
We'll look like this, and so this is 5 minutes until the talk. Then there is extra 5 minutes for questions. So this actually means that there's 10 more minutes for whole like talk plus 5 minutes. Okay.
Can you see how?
Okay. And how do you pronounce your name? Like. Thank you. Yeah. So is there any other? No. Gregorz. It's fine. Gregorz. I think that's the best I can go for.
Yeah, I understand. This is really hard.
No, Casper is easy.
Yeah, Kasper is probably easy, but
Kasper knows.
yeah, it's Grzegorz is like one of.
Yeah.
There's so many Polish.
We have in our group someone named Gregorz, and we call him Greg. So like.
Yeah, that's the
short version,
equivalent.
like,
So.
When I communicate in science with some older professor, I call Greg.
That's easy.
Yeah. Also, if you want to if you feel like you need like 2 more minutes, you can just go on, and then there will just a little bit less time for Q&A. Very stubborn. The one thing you can do. I was told that you can try to stand up and maybe slowly walk towards them, and they will know that they should probably. So for the but I think we managed. Why they didn't let us know that there was this change in schedule. That caused the problem.
So hello everyone. We are here. Our next speaker, Gregorz. I hope I'm pronouncing it well. And he's going to talk about from code to app. So let's welcome the speaker, and the floor is yours.
Okay, now it's microphone. Okay, so hello everyone. I'm Grzegorz Bokota. I work in Pari as a core team member. I am also working on the university, teaching people Python. And today what I would like to talk is, okay, you wrote a program, you have some of your code, and how to ship it to some other people. So Napari, you could see, maybe some of you see our stand in the next to the coffee. We provide the viewer for n-dimensional data. I could call that we are integrator for some of data scientists who are working with special data and wanting to visualize them, visualize some annotation over this data to check if it's working properly, or maybe to allow their colleague who are not experts in programming to also play with the data without their help. So you might come to us and ask some more questions, but also this is the project for which I would need to learn about what I was talking today. Because once we would like to ship the whole application with Python code to people who are not programming, the cases like, hey, just set up Python on your machine and then type something, it's not working. So, okay, so initially, I would like to do some introduction, more maybe not, I'm not sure what is your experience. I will talk a little more about motivation. I will talk a little about packaging, because if you need to ship something, you first need to do the same steps like for a packaging. So building a package that is pip or conda installable. And for bundling, I will talk about two tools that I'm most familiar with. So it is Py installer and conda constructor. So, okay. So what is the most common, from my perspective, most common workflow if you are a bioinformatician or some expert, but you cooperate with biologists or other domain experts who prepare data, but don't know how to program, don't know how to massively process the data. Okay, in an ideal world, we start from getting sample of data. In real world, we often get final data set, and there is a ask, you will do this in 3 days. Okay, so when we have data, we have some project description, because we need to know what we look for in the data. This is something which is not always, not all people, expert domains are thinking that, oh, I just give you a data and you will give me a result, but I don't tell you what I expect. And here, this is what I expect is the big problem, because it sometimes happens, even if there is a biologist and there is a bioinformatician, where theoretically bioinformatician is learned how to understand biologists. The biologist is so diving deep in a given part of biology that language that he uses is not easy to understand for a biologist, for a bioinformatician or some other biologists, and it's totally not to understand for people like me, where I'm a computer scientist who come to the working with such a data, and with my lack of some knowledge of biology is problem. And the final step is adjust workflow parameters to data. It theory sounds simple. In practice, it can't be long hours of this type. So the technical expert is sitting and adjusting some parameters, and domain expert is trying to explain what he would like to achieve, or she. This is the better case. The worst case is that they come on some meeting and told that it's your fault that the result is not as expected. Even if they do experiment, and there is no these results in the data. But what we would like to do is to, okay, here you have interface, you could adjust the parameters, you could play as long as you want. There is not such a thing that we have only 1 hour meeting. You know, you could do this as long as you want without any problems, play with it, see the results. Maybe next time you will come with the sample of data and we could discuss the procedure of collecting the data, that maybe you just a little change the experiment, and instead of wasting many hours, you could just extract the information from the experiment, because you measure one additional parameter which you think is not needed, but in reality it's really needed. So this is what we want to get. Okay, so first step to be able to ship, because you know, you might see on some computer, I don't see this in this room, but I was on the last week on EuroPython, and some guys has the sticker on their laptop, it works on my machine. This is some solution, but I personally prefer to not give my machine to someone. Okay, It happens to me. It happens to me that I prefer to just give someone my machine and told, here you could sit behind this computer and work on this data. But the better situation is that I could ship the application on his machine and don't care about this problem. But if you would like to give a program to someone's machine, and we don't work on the just simple case that we depend only on Python standard library, or even if we can depend only on Python standard library, there might be some feature which is introduced in some newer Python version. We need to know what is required to be installed. Of course, there's a big power of notebook, physical notebook when someone knows everything, but it's really not useful for purpose of synchronization, etc. And Python community developed it a long time ago. This is the packaging. So this is the formal description of package, what it contains. It contains some metadata for a human, some metadata for installation, like required dependencies, optional dependencies, supported Python version, package version. And this is really important metadata. The package version is really important metadata because it happens that someone reports you a bug that is already solved. And only by package version you could see that he is still using old version. You wrote him an email 2 times, please update to the newest version, and he still uses older version. So don't forget about bumping version anytime you send it to someone to know what he is using at this moment. So it is a package and you could just give it. This is, so as I told, formalized way. So the important is formalized. It's supported for toolchain. You don't need manually open a file and then type some commands. From your perspective, even on beginning, it simplifies changing machine. I meet on few conferences people who have a problem that they have a great package, but they have a great workflow, but it works only on a single machine. And they look on their notebook. They try to use their physical notebook, but they cannot reproduce the environment on second machine. They don't know which step is missed. But also, it means that if you update your package because of some feedback, you could easily send this, just execute one command, and if there is a need to update some of dependency, it will be updated. You don't need to manually, okay, you have here new code, so you download it, unzip, put in this directory, type this command, do this and do this. So many places to know. Download this, pip install path to this, it's done. And also, when it's standard, there is a great tooling around it. Multiple things could be checked, multiple things could be validated just by checking. So other stuff that might be important are reproducible environments. There are multiple ways in Python world to freeze what is in the environment that you are working on. Because often if you have constraints, there's a lower constraints, not upper constraints. It also simplifies if you sometimes would like to move from one machine to another to reproduce. It's not the star from reproducible. It's not fully reproducible because if you, for example, change from Intel machine to macOS ARM machine, there are differences in the float calculations. Even at last, we meet the problem that on the AMD EPYC processors, there's a slightly different results on float calculations. So you install this allow to install exactly the same version of the packages on the different machine. It do not mean that you will get exactly the same results. It could differ on the different levels, on the processor level in some situations. On the bugs, it might happen that the given, for example, NumPy version, NumPy is not a good example, but some more niche package is working great on Ubuntu, but there is a bug on Mac or bug on Windows, or it works great on Windows, but there is a bug on Ubuntu. So this is not fully reproducible, but still, what is option? The oldest one, constraints.txt, is just a list of, you could get it from piplist to get what is in your environment. More modern UV-lock, and I know that there is a work on introducing locking mechanisms to pip also. The environment YAM is Conda way to inform what is in your environment. Environment YAM is more pinned to the operating system. It pins, for example, some packages that, oh, install this in Linux version. But for the Conda world, as a UV lock is for the pip world, there's a PXE lock, which also produces some log file which could be used not only on one machine, but only one operating system, but for more. So what are packaging methods? So this is also, so from the starting, maybe most familiar for most of you, the Python package defined in PyProject.tom. This is Python package, so it's finally it's installable using pip, and you could import from it. UV introduced workspace. Workspace, it could be Python package, it could be just set of scripts, it could be Python package and set of scripts, many things. So it's a little more generic. If you use UV workspace, you could easily convert into Python package. You could easily just add two lines, and then you could build a Python package that could be uploaded to PyPI if all data are properly metadata are properly specified. And for Conda world, there could be recipe.yaml, or for some older packages, it could be still meta.yaml. It depends if you use Conda builder or lateral builder for the package. But it's similar to PyProject.tom on PyPI, for PyPI packages where you describe the dependencies, where the dependencies should be installed from the Conda. Okay, how many of you know what is the Conda? Okay, so many who not know, because it looks like, okay, everyone knows, okay. So I see that almost okay, so I don't need to explain. And the PXE also allow to provide both package and workspace using either PXE.tom or PyProject.tom. The PXE.tom is also nice. I learned this, that you could store most of the information about your package in PyProject.tom, which could be used to create the package that could be uploaded to PyPI or just send it as a will to someone else. And then just additional stuff in the PXE.tom to not interfere with PyPI. Okay, so short overview. The Python Star package, there's a, if you may remember things like setup UI file, setup CFG file. It is the old way. Now there's a decision to store everything in the PyProject.tom. It allows to select build backend because setup CFG and setup UI are connected with setup tools. There were also other for poetry and other stuff. So for this one, if you describe, it's expected that you produce a package. So something that could be importable from other places. And what you could provide some human readable metadata, like, okay, I don't see. You see, the project section is mostly human metadata for human. The only thing which is for the machines is the Python required Python version, but it's also for human. But below you could have the things like dependencies. So what is required for the to build the package is only on top of a sample package, because you now below could have extras, so the optional dependencies and other stuff. And such created package could be easily installed by using pip, UV, or PXE. So it's useful. I will talk a little later about this. UV workspace, you see, if you compare, there is a build system on the top of this, and on the UV workspace, there is no build system. If you add it, you could convert it to this what we talked a little earlier. But if your project is just set of notebook, and the persons are enough brave to use notebook, they don't just know how to make them. But you know, in the notebook, you could have even the GUI elements. You could use workspace where you could define also dependencies, but there is no need to create a Python package from it. Conda package, different way, but you define the same basic. Here is the example based on the Conda forge. So you have from where you get source code that is for Python without specifying what is required to build, what is required to run. At this moment, you cannot store such many metadata for human like classifiers, like this stuff, like in the standard. But I know that there are some works to change this. And Pixie is trying to connect both Conda and PyPI world. You could mix the packages. You could tell on which operating system you would like to support your workspace or package, and pin dependencies. So when I was talking about making the installer. But for many of you, maybe creating a great package with some small additions could be enough. Because if the target user is your friend who is sitting 2 desks away from you, you might just go to his computer, create environment, install your package, and create a shortcut on the desktop. And he will not know that there is some Python underneath. And also, if you need to update, you have environment, you could just install the newer version of package, and it works. So in many situations, especially with most recent hardening of an operating system because of rising viruses, you should consider this. But in many situations, I would like to tell that you should start your work from beginning using when packing it as either workspace or Python package, because it's much easier to change the computer, to go back to this work, to be able to have reproducible science or reproducible other work. So as I told, yes, it's possible to just using the standard bat script on the Windows, the desktop on the Linux. I don't remember Mac name, but also it's possible to just create a shortcut which under the hood will activate the Python environment and then run a command from it. Okay, but now let's go to the topic. So no, we cannot do this. For example, we need to ship a code to someone who is sitting in a different city, or like Napari, we don't know who is using it. We just want to share with our work to multiple people. We are brave enough, and we are thinking it's useful enough. So we would like to build a bundle. So the first thing that I would like to talk is the PyInstaller. It's easier solution. You see the link to the web page. It tries to collect all modules required to run a package. It might fail. We'll talk about it later, but it tries to collect this. It is portable installation. So you just get a zip, unpack zip, go to the proper place where the executable is. So you need to go inside the unpacked directory, and there is an executable, you could just execute it. What might be important for some of you, it do not encrypt code, but hide this code inside the binary. This is advantage and disadvantage. You cannot just open, when you download the PyInstaller, you cannot just open it and read the code. But of course, it's not encrypted, so the code is present here. Okay, so PyInstaller takes as an input the script. Just simple script, and to create, initially to work with PyInstaller, you just wrote PyInstaller script. So let's see. It's local, so it should work as a demo. Okay, we have here app UI. So we see the simple app that just import NumPy and read the inversion of some matrix. Just simple, but it requires something which is not in the Python standard library. So I just Give us a short moment. And when we see again, you see that there is a dist directory. In this dist, there is app, so I could just dist app, and it executes this code that we see earlier. So, but there's if any of you have at least the same version of macOS that I have, I could just zip this and give it to you, and it should work. This is for the both tools about which I will be talking. You need to have each operating system to build a bundle. But, for example, we build on CI. We don't build locally, we build on CI, every time fresh environment. Okay, that's the next section. Because this is a simple application, so it works. It not always works, but as everything. So there is a second app. This, if I wrote this second application, it behaves exactly the same as the first. But if I use PyInstaller, it generates, then this it crash. So where is the problem? The problem is in this line that I import using import lib. So it did not detect. How I could solve it? I could solve it hidden import. Okay. So I told that, okay, this import is missed. You will not most often have this, but many libraries are using hidden imports to some speed up or some other stuff. I would like to replace. Now it works. So okay, it's just okay. So going faster. PyInstaller is not bundling all libraries that is installed. It just follows the path and try to minimize the size. It happens that it cut too much. Non-standard imports are omitted. You need to add it with hidden imports, and data also are not omitted. PyInstaller are giving you an option of providing one file executable. I will told now you should not use it. Because how it works, it just unzips to temporary directory and start application. Where is the problem? Every time you start application, the new executable shows for antivirus. So Mac, Windows, or maybe some Linux will just scan application on every start, increasing the start sometimes up to a few minutes. And if you just ship the unpacked version, the first start will be slow, but then it will remember, hey, I have seen this file, it has the same checksum, I don't need to scan it again. And because it bundles this, every time you need to rebuild it. From bigger application, it takes time. Okay, so other stuff. These hidden imports allow you to ship the part of the application as a code. But you told that PyInstaller this code is the data. So you could just put Python files inside and it will work. Important thing, if you're building, keep environment locked. Because you would like sometimes your new build will fail. And if you don't compare to previous environment, you don't know if it's changing your code or changing some package. And what I could, from my experience, embed some simple tests inside the application to check if everything works. 2 minutes more and It's built for environment separate, so keep separate environments for building. There's a Pi update. There are some other alternatives like Mutka. I don't test them deeply. And if you spot some problem, there are options to provide hooks. If you are package author, you could provide an import hook or data hook in your project. If you are user, you could use the contribute to Pi installer hooks contrib with information how the library should be embedded. Okay, Conda constructor, 2 minutes and Conda constructor is totally different. It ships the whole Python environment as a Conda environment. It's for complex project. It's setup which is expensive, but it allows you to modify everything after installation. You could have Conda pip inside. You could make Conda install, pip install inside. Could update inside easy. So what is the basic steps? You need to create a Conda package because in PyInstaller you might have a script. You don't need to have a package, but it's nice to have workspace or package to keep the metadata required to collect dependencies. In Conda, you need to have a whole package. You need to have some additional construct YAML file, run constructor, ship installer. Someone need to install it. Installer is downloading data from web. When you do this with PyInstaller, it is just download and run without needing to download anything if you don't embed download in your code. Okay, so Conda installer much more depends on the Conda world. It is useful for our case because in our community there are some packages that are only on Conda and not on pip. It's more complex, and there are alternatives like Briefcase. Okay, so maybe that's all.
Thank you for the talk. The session is open for questions.
Many thanks for great talk. Could you please kindly try to provide pros and cons between idea to delivery as Docker image or at least Docker file compared to executable Python code?
On Docker file, you have isolated things. So if you would like, for example, ship web server, yes, it's better to Docker file because it's isolated. If you would like to ship something like Napari, which is GUI application, you cannot use the Docker, but also this application have access to local data, local other stuff. So if you would like to ship something which is standalone and not GUI, Docker may be good. If you need to something which interact with your whole environment, then executable.
Any more questions?
So a problem that we face quite often is that the collaborators that I work with have really basic computer knowledge. So an exe file is the only option that I can ship program code. You mentioned the problem with the antivirus, and that's something that we also face because we cannot make any exceptions in that regard, at least in the system that we use. Do you know of any other workaround to speed up the execution of a software like that?
There is this signing code, which I don't have time to talk.
Oh, okay.
If you get a signature from Microsoft, proper signature, you could sign your code. It means that it comes from a trusted publisher, and in many situations it helps.
I see there are no more questions, so let's thank the speaker once again. And please stay tuned. We have now a poster spotlight. So people who are here for the poster, you can start.
Okay, we can have a short break, but we'll have a presentation from poster presenters in just like 10 minutes. So if you'd like to see, please come back or even stay. Yes, yes, here. We'll have a short presentation.
How long?
It will be 20 minutes. That's it.
Just go.
Yeah. So it's here. You can leave it here. Yeah.
Okay, hello. Uh, Hello, everyone. So this will be a very short poster spotlight session. Speakers will have 2 minutes just to briefly present the entire topic of their posters. The posters are visible near the room 119, and you can view them today, and I believe tomorrow they will also be there. So we'll start with the first presenter, Mike.
Mike needs a mic. Okay, great, thanks. Okay, that's me, Mike Müller. So you might have seen me around. I have two hats, only two hats here. So Python Academy is my Python teaching, and High Tech Computing is the company that's that the poster is about this water stuff. You might if 2 or 3 people have seen the talk in the morning. I also have another hat. I'm also the chair of the Python Software Verband, but that's here the poster. Good. And this is, again, a coupling thing. I tend to couple things, and I couple numerical and analytical groundwater models. So most of the time when you do model the flow in the groundwater, you numerical model, which it's very, very powerful. You can do a lot. The thing is, it calculates very long. And sometimes you have very long computation time. You need to have very small elements to do this, a lot of data. The other alternatives would be analytic data. They have a very nice mathematical analytic solution. The problem is they're only there for very specific use cases and not general. But solution is you use both of them. So you use a coarse numerical model, and then for the detail, for some details, you can use analytical model. So the numerical model has a space categorization at points. An analytical model is continuous. You can have at any point in space, you can model it. And I combined it here. And I use the same approach as in the morning, this Mod46 coupling thing I showed. Mod46 is a numerical model. And I couple analytical model, which is TTIM, which is a Dutch product. So some Dutch people here, Dutch are very good in this AEM, it's an analytic element modeling. So they use this analytic method model. So I didn't invent any of the numerics. I just put together and made something new. And then at the end, you have something that looks like this. You see, this is the squares. This is the numerical stuff. Usually a real numerical model has way more of these square cells. And then the other ones, the round ones are, these red cells are defined with analytic models when you do analytic models. Thank you.
Next up, we have Vyron Vasilaitis. Do we have him here? If not, we'll continue with Ernestas Simotis. Big round of applause.
Hi, everyone. I work at the TU Wind in Denmark in a research lab, and we are doing systems engineering and optimization. It's mostly working on wind farm control and layout optimization. Like you can imagine, if you have a wind farm and a bunch of turbines placed in there, it takes one turbine takes out energy out of wind, and then downstream turbine has some losses. So you basically try to design your wind farm, including these effects and optimizing annual energy production. I just have a poster about Pixwake. It's basically like a rewrite of one of our core libraries, and it's just basically rewritten from NumPy with Autograd. It also has QPy support. Although QPy doesn't interact with Autograd, so and we are rewriting it in JAX. And basically, if you're interested in like porting native NumPy code with Autograd into JAX, you can talk to me. Yeah, and it's just used for, like JAX as a used for general numerical computation problems instead of like doing machine learning, which is like, I guess, the most popular application of it. And I have another point about stochastic constraint optimization. We have developed a novel optimization method where we can take samples of big model computations and speed up the optimization process quite significantly by just taking like a small batch of model samples and doing quick optimization steps, like converging much faster, like compared to like a regular oscilloscopy where you take a full model gradient.
Yeah. Thank you. And next, we have Stanislav Jaroszyński. No, also not present. Okay. Next, we have Agria. Big round of applause.
Hi, folks. I am Agriye, and I'm a software engineer at Quantsite. I mostly do open source scientific software for a living, but I'm also on, I serve as a member of the NumFocus Security Committee, and which helps a lot of scientific software projects in the NumFocus umbrella deal with security issues and like with providing recommendations and so on and so forth. So my poster is about security, and it's about the Shai-Hulud worm and its interactions with the scientific Python universe. So the Shai-Hulud worm was introduced through the cult classic Dune book series and its popularized movie adaptations. And the worm is essentially about how a particular vulnerability in your software travels through the software supply chain and affects a wide variety of different sorts of projects. And this was originally within the JavaScript ecosystem, and we all have some sort of reservations with JavaScript. But Shai-Hulud is actually now attacking a lot of scientific Python projects, especially this year. So I would like to, within my poster, the thesis is that this is an adoption gap and not an invention gap. So all of the tooling that is required to prevent this sort of supply chain attack already exists. So so the poster is a medley of all these sorts of resources. And this is the masthead of the poster. It is based, again, on a Dutch product. So based on the art of Piet Mondrian. And so I haven't included the full poster because I think it's useful to have a bit of suspense. So you can use this QR code if you want. So thanks for listening.
Thank you. And now we have Gracian Adamus, who will be also substituting for a second presenter.
Hello, my name is Gracian. I'm a student here at AGH and also this year's summer student at CERN. My poster will focus on PyPartMC, which is an open source package for atmospheric aerosol simulation, which is an interface to PartMC, which is a big Fortran package that has been developed for 20 years. In the poster, I outline how you can call that compiled code from Fortran through Python, how to keep such a multi-language code base maintainable, and how to even use it with the same API from different languages. And if you want to learn all that and more, please swing by my poster. I will be happy to provide all the details that I was not able to fit in the poster. Yes, and to quickly substitute for my friend who could not be present for the poster session, he presents a poster on his approach to deepfake audio detection with an AI model. And basically in the poster, you can see the dataset that he used, how he did the training, and his results.
Thank you. And now next we have Sudipta Ghosh. Do we have the speaker present? I believe not. I'm not sure also if Michaela Miller. Yes, we started with Mike Miller. We are ending with Michaela Miller. Big round of applause.
Refresh the slides because I just added a second.
Okay.
Refresh the slides. That's fine. Two slides. Just like escape and then we share.
Yep.
Okay.
Thanks. What? Let's do it like this. Now it's you first.
Yeah, good point. Okay, cool. Yeah, thank you so much. Hi everyone, I'm Michaela. I'm a PhD student at Helmholtz Munich, and I wanted to talk about a project of mine. So I come from the single-cell biology field, which I'm not going to bore you with the details. If you're interested in this or familiar, you will know. And you can come to my poster and we can talk. But what I wanted to present today is a tool that I built for the single-cell community that actually solves quite a hard, in my opinion, quite a hard engineering problem. So in single cell, we have something called atlas building, which is basically building a resource that people can use. And this building process is quite iterative, as in like many scientific questions. And I just want to kind of abstract the problem on the left-hand side, that you define the scope of your problem. You go into like something called integration strategy, which involves multiple different questions about the data and how you want to pre-process your data. You run a couple models. You evaluate whatever the model spit out, and then you refine all of your pre-processing because you now understand your data better. And this is a big iterative process, and to some degree, you might even need to go back to your original question and adjust what you were looking for, what you were asking. And once you have like a good representation of your data, then you can look at more downstream questions. So this whole process requires a lot of flexibility. And also, I think something that people might underestimate sometimes, also good model evaluation. So there are a couple of features that I developed and built into a toolbox called SEAtlasTB. One on the model evaluation. I came up with a couple of new metrics on how to compare the structure of the local structure of data. That might be interesting to some people. Then I think a very big paradigm shift is to kind of go from coding. Instead of coding your workflows, you actually go to configure your workflows, which helps a lot for the user to actually focus on what they want to be doing instead of worrying about bugs. And of course, there are a couple of scalability optimizations that I included. So GPU support, out of memory support, and also very smart file storage improvements. Yes, and in summary, I just want to kind of say that, yeah, we're in need of a very flexible and scalable framework, and the toolbox basically provides an agile framework from the user side, very scalable functionality, and yeah, and a way to actually optimize your problem, your scientific question in a data-driven way. Thank you very much.
Thank you, everyone. Big thanks again for the presenters. That's it for today, unless you bought a ticket for a social event, which I would like you to remind you, it's at 7 and at Restauracja Galicyjska. And tomorrow, I believe we begin at 9:15 with the opening announcements. Karol, you wanted to say something? Yes?
So exploiting the fact that we have quite a few of you here, we have just one announcement for tomorrow. When you enter the lunch area, please make sure to read the labels near the food, as there is a separate option for people with, vegan-based diet, and separate option which is for people with meat-based diet. So please make sure that you actually take the food which corresponds to the diet that you chose while registering, because we want to avoid the situation that someone signed up for a vegan diet and then the vegan food is already gone when they come to the counter. So this is one thing, and the other thing, probably heard me shouting this also during the lunch break, but if you require a gluten-free diet, there is also a separate meal packed for you once you enter the lunch area. If you can't find it, just reach out to one of the organizers who will point you to